So let's have a look at this one. This is another read the question. Right. So, Max Locke is trying to get two computers numbered 0 and 1 to share a printer. They control the input signals P0 and P1 respectively. Is this a new question to at least most of you? Respectively, in which they send 1 at time t if they want to print at time t plus 1. So that's the idea. If they want to print, they send a 1. This is quite a lot like Xavier and Yvonne, but not exactly the same. If they are not competing for the printer, then both computers should get what they want. Once a computer starts printing, it should keep the printer as long as it wants. If neither is printing, but suddenly both ask to print, the computer which printed most recently should give way. So that's to say, we need to remember whose go it was last time so they can take turns properly. So the unfinished diagram below, so here we go, here's the unfinished diagram, I better zoom out there. Shows how far Mex has got. It's got a D flip-flop with output Q and a JK flip-flop with output Q prime to be interpreted as follows. Then it says, if Q of T, so that's the output of this D flop, if that is 0, that means nobody's printing. But under those circumstances, the other flip-flop should tell us who printed most recently. Okay? If Q is 1, that says somebody's printing, and then Q prime should tell us who is printing, 0 or 1. Okay? And there's a special clue designed to make your lives easier, even though it looks like it makes the circuit more complicated, is that MEX uses muxes to isolate the situation where the computers compete for the printer. So this is a situation where circuit might look scary, but problem gets easier. Remember, muxes cut up problems. Right, so we're saying there's two separate things going on. There's what happens if they're not competing, and which has an easy logic, and there's what happens if they are competing, which has a different logic. So let's first of all, we're being asked, we're asked for some book work. I'm trying to give 2 marks away on characteristic tables for D and for JK. I'm not going to do that here. I'll just do the interesting part of the question. And then we're asked to use whatever gates we like to fill in the missing boxes. Okay, so let's have a look at it, right? Remember, this flip-flop says whether somebody is printing or not. And then this one says either who is printing or who printed most recently. If you look at what's going on with the muxes, remember that a mux uses its first input to select between the other two. And you can see that both muxes are controlled by this AND gate, which is connected to the two inputs. So that's to say, so remember P0 and P1 are the inputs that say that each of the printers in turn wants to print. So this AND will be true if both want to print. Okay? So now let's see what's going on. One mux controls J, the other mux controls K. And you can see that when both want to print, we'll take the third input of the mux, which is coming out of this box here. And that goes into both J and K. Does that make sense to you? What does a JK flip-flop do when it gets two zeros? It stays the same. What does a JK flip-flop do when it gets two ones? It toggles. What we're saying is that when both printers want to print, or when both computers want to print, who actually gets to print should either stay the same or toggle. Right. One thing's for sure, by the way, when somebody wants to print, if anybody wants to print, some printing better happen. There's no reason to say, somebody wants to print, no printing. Out of paper maybe, but no, I'm not going to let you. Okay, yeah, so let's work our way through the, one more thing, yeah. So if it's not the case that both want to print, then the two muxes, J and K, are taken from the middle input, which are coming from these boxes. So these boxes only have to do the right thing if there's no contention. And they control set and reset. So these two boxes are going to decide what happens if there is no contention between P0 and P1. That's all we have to worry about there. Okay. So let's think it through. Let's start with this box. Right? So Q should become true. Remember, Q tells us if somebody's printing. Q says printing on or off. When should that happen? What's the logic? We get told what do we get told? We're told if they're not competing for the printer, then both computers should get what they want. And then the rest of it says, it explains what happens if they are competing. But certainly that's about deciding which one gets to print. So how do we express that if either wants to print, somebody gets to print? Or. So this, remember, the D input is going to set the Q output, right? Q next time is the same as D this time. So the right logic to say, should somebody be printing next time around, is, does anybody want to print this time around? It's as simple as wiring both of those to an OR. You see, that says if somebody wants to print, then enable printing. If nobody wants to print, no printing. Okay. Now let's think about these two boxes here. Right. Key message. The muxes ensure that these boxes don't matter when there's competition for the printer. So for the purpose of constructing these circuits, we can assume that if one printer wants to print, then the other one doesn't. Because in that situation, the last box is going to call the shots. Okay? So we get access, we get to control, so we're in that situation. Let's actually, we can even write a truth table for this part. P0, P1, we're interested in controlling J and K. And we're interested only in the situations, in these three situations. Yeah? The situation where both want to print is handled somewhere else. So these are the only interesting situations. Okay. If nobody wants to print, what should the JK flip-flop do?
Return 0.
It shouldn't return 0, because remember, the instructions say that if nobody's printing, then it should remember who printed last. So given the things that JK flip-flop can do, which should it do when nobody wants to print? It should stay the same. It should remember what it was remembering last time. It should keep remembering who printed last. Okay? How do we tell a JK flip-flop to stay the same? 0, 0. All right. Next situation. 1 wants to print, 0 does not. What should the flip-flop end up doing? Who's going to get to print? P1. That means the flip-flop should output what? Well, no. It should tell us the number of the thing that wants to print. And we've decided that the thing that wants to print is number 1. So we want the flip-flop to become 1. How do we tell the flip-flop to become 1?
Send the 1 in J and 0 in K.
That's correct. We send it unambiguously the set signal. Okay, how about the last case, where number 0 wants to print and number 1 doesn't? What should we tell the JK flip-flop to do? We should tell it to reset. How do we tell it to reset? 0, 1. All right. So now we need to build some circuits that have this behavior in these boxes. And we don't care what they do in the 2 1s case. How about the circuit controlling J? Any suggestions? It's exactly P1. How about the circuit controlling K?
P0.
It's exactly P0. Okay, so the hard part of this problem is figuring out how little you care about when you're filling in these boxes. Yeah? Is realizing that the muxes are making it easy. All you're saying is, what you should do if there's no problem. Drawing the truth table is useful from that point of view. Could have written P of t. Maybe I should have written a q prime of t plus 1 column, just to say what we want it to be. This should be q of t, this should be 1, and this should be 0. That's what we said. Nobody wants to print, we should remember the last q prime of t. We should remember who was printing last. Printer 1 wants to print, go to 1. Printer 0 wants to print, go to 0. These are the behaviors we want. These are the signals which produce that behavior. So it's figure out what the behavior is, figure out what the signals are that produce that behavior, figure out what the circuitry is that produces those signals. Always working backwards from desired behavior through to the circuitry we need. Okay, so last part of the problem is exactly to say whether or not, we figured this out, that this circuit is basically saying whether or not to toggle. And let's think about it. Toggle or not. Let's draw a table. Let's see. We've got access to Q and Q prime. And we're supposed to figure out what we're going to set. Well, what Q prime of t plus 1 should be. But we need to remember that we can only send basically a toggle or not control out here. Does everyone see why that is? Can everyone see from the wiring and the behavior of mux why the signal that's here, which is coming in, so if I just double down on this wire, so you can see that is the signal which goes into both J and K when this AND gate gives us a 1. All right. Let's figure out what we need to do. But hopefully it's not going to be all that tricky. If we're in the situation where both want to print, but remember, what does Q tell us?
Somebody's currently printing.
It tells us whether somebody's currently printing. Okay? So in this case, we've got 0, 0. If nobody's currently printing and both want to print, who should get to print?
The opposite, the other person who wasn't one who printed last.
Yeah, the other way around. If nobody's currently printing, then we know this is telling us who printed last. And it should be the other one who gets a go. Whereas in the other two lines, we're in a situation where there was somebody already printing. And this tells us who. If they were already printing, who should get to print? The words in the question do tell us. Once the computer starts printing, it should keep the printer as long as it wants. This is telling us that they are already printing, that somebody's already printing, and we know we're in the situation where both want to print. That in particular means whoever was printing still wants to print. So what should happen? They get to keep the printer. Okay. Can we see from this the logic of whether to toggle or not? So we just figured this out, that when Q was 0, we're going from 0 to 1 or from 1 to 0. In both situations, we would like to toggle. So, yes, toggle. And if Q is 1, we would like to stay the same. So does that tell us what needs to go in this box at the bottom? So certainly there's a not. Which thing shall I not? Well, this is what we want Q prime to be, but remember the signal we're actually controlling is whether or not to toggle. No. So we're trying to generate this signal.
Not Q of T.
It's just not Q of T. Remember, what we're actually controlling is not directly the value of Q prime of T plus 1, but rather the signal that will cause it to take that value. So we've got to encode the correct instruction, which is toggle or not. And there's a bit of a clue. There was a lot of the clue, a lot of this question was set up for you by the way in which the muxes cut up the problem into dealing with the contention or the lack of it. So it's one of those situations where the circuit might look big, but there's some method to it. So rather than just saying, oh, that looks big, instead try and ask, what's going on? Assume that there might just be some benevolence at work. I might be trying to make the problem easier by cutting a problem up. That's usually what happens when you see a mux in a circuit. You should think, how is this cutting the problem up? What's controlling this mux? And what difference does that make? We're talking, we're saying we're managing difference between two sorts of circumstance. And then once we've figured out that we're dealing with two different circumstances, the logic of what do we want to happen and how do we tell it to happen wasn't so bad, really, was it? Anyhow.